So I'm starting this session, started the recording. So you all can hear my voice, right? Okay, fine then. Okay. So the first question is to join. Okay. So everybody can see my screen, right? Am I disconnected? I think so. Did somebody respond in the chat? Because I don't know if I am audible to your people and you all can see my screen. Okay. So let's start with the first question. So which of the following polymers has random arrangement of side groups? So uh, the answer is a atactic polymer. I'll just mark the correct answer itself. So if this is these are, let's say, the carbon atoms, polymeric chains, right? And this is how the chain goes. Repetition of monomer units. So this is the case. Also, let me just draw one more and two. So these are so so, so these are the carbon atoms. So these are the carbon, right? And the dispersed are hydrogen atoms on top of it. So hydrogen atoms are also dispersed like this. Okay, so like this only. Let's say like this, and also like this. Like this. So repeating it. So repeat like this. So these are the hydrogen atoms, right? Now for atactic polymers, okay, somebody wants to join. Okay. Okay. So now the side groups, which are, let's say for this case, which can be the vinyl side group, let's say for chlorine. So they're randomly dispersed or they're randomly distributed, these side groups, right? So in that case, you'll have a completely random distribution of this side groups. Okay, so it can be here, it can be here. So for atactic polymers, so for atactic polymers, the side groups are randomly arranged. So for this case, we have this vinyl subgroup, side group, the chlorine, or the vinyl side, right? This is really simple. So for atactic polymers, So for adaptic polymers, you have this random arrangement of side groups. Now coming to the next question, the question is the repeating units in nylon are linked together by which? So just for repeating it, for the sake of repeating it, you've already seen in the video. This is a fairly simple question, but I'm still drawing it. So this is CH2, CH2 pretty long chain. This is C, this is N, this is CH2, this is again CH2. So these are repeating units as you can see. CH2, this is CH2 again, CH2, and sorry, also just so it's not complete. So let me just draw it again. And this I'm reading that if you have any problem in between, please just interrupt and ask your questions. Feel free to ask your questions, alright? Because this is not just knowing the answers and putting it, submitting it, and this is not a case. So you have to learn. So this is the nylon chain. So this is CH2. This is again CH2 such chain. This is CH2. This is N. This is nitrogen. So basically, this again is another chain. So this is CH2, C, N. Okay. CH2, 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 this is CH2, this is N. This is C, this is CH2. So now this carbon and nitrogen is bonded by oxygen, okay, and double bonded by this hydrogen, right? And again here you have nitrogen, you have this double bonded, this hydrogen bonded oxygen, and again double bonded carbon. So these are the hydrogen bonds, right? Hydrogen bonds. Also goes similar, right? So now if you look at this group, this is your carbon, nitrogen, and bonded by this. This is your amine group, right? So the parallel chains, they are like this amide group in your nylon. So basically your answer would be the amide group. So carbon double bonded oxygen, your hydrogen bond is there, and there's nitrogen in between, and your repeating units, the CH2 monomers, in case these polymers, they are the repeating units, so that forms your amide group. So the repeating units in nylon are linked together by this amide group. Okay. So now, so chat box, if you all have any question. Okay, fine. So you all can hear me, right? Okay, fine then. So is it a bad network problem from my side, because I'm not able to understand if that's the case, because will be okay. But then it's fine. It's not an internet issue, right? Yeah, yeah, you're audible. No, I was thinking maybe if I my network got frozen or anything like that, because in between when I'm teaching. Yeah, 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 yeah. I thought it was my internet problem. Okay, okay, fine then, fine. Okay, okay, fine, fine. Okay, then so okay. So the next question is regarding the vulcanization of natural rubber. So natural rubber, I would say, like this natural rubber. So basically, isoprene molecules. So these are pretty simple questions. But anyways, this carbon, this hydrogen, this is hydrogen, this is hydrogen, this is hydrogen, this is C3, this is your project, this project. Okay, and now this is hydrogen, this is hydrogen, this is carbon, CH3, CH. So this will be occupied by sulfur, right? So I've already given the answer. Like vulcanization of natural rubber takes place by its treatment with sulfur. So after vulcanization, get this form. This is carbon. This is hydrogen. This is again hydrogen. This is carbon. Initially, this double bond should now be a single bond, as you can understand, because sulfur is there. So carbon. So this is CH3. This is carbon. This is hydrogen again. This is your sulfur again. Okay, right. So initially it was double bond in this case. So now it should be a single bond with sulfur, because sulfur is replaced. And again, you know, this carbon, this is hydrogen, this is hydrogen, this is carbon, this again was a double bond previously. So now sulfur has been replaced by this. Now with CH, C, okay. So these are crossings. So these are basically your crossings, right? So treatment during vulcanization of the molecules of rubber treated with sulfur so that it gets hardened. Like the rubber is pretty hard. It's not like a conventional glaze or rubber band sort of thing. It is pretty hard, like board, as you can understand. I used to seal your chemistry apparatus. These all are very hard. So that those are treated with sulfur, right? And they become extremely hard. So because of the cross linking with sulfur, right? Okay. So the next question is which of the following? So let me just check box this with. So the vulcanization of natural rubber takes place by its treatment with sulfur. The fourth question is which of the following is or are correct for polymers? As you can understand, this is a multiple choice question. So thermoset polymers soften upon heating, which is not the case, which is actually the opposite. They harden upon heating and they become brittle and they can disorient and they can decompose. All right. The second option is vulcanized rubbers, epoxies, and phenolics belong in the same class of thermosets, which is true. Okay. And cross-linking is the characteristics of thermoplastic polymer. So as you can as you've already noticed in the last question, that for natural rubber, thermoplastic polymer, cross-linking is the characteristics. So cross-linking has to be there. So this is correct. Thermoplastic polymers have linear and branch structure. This is also not true. So the right answers would be vulcanized rubbers, epoxies and phenolics belong in the same class of thermosets, and cross-linking is the characteristics of thermoplastic polymer. Alright, so the electronic transition, the next question, the electronic transition taking place from M shell to K shell emits which of the following characteristics of X-ray radiation? Alright, this is an interesting question. So these are interesting questions apart from the monotonous, very informative sort of questions which will be so let me just draw the so the shells. So this is the N shell, this is the M shell, this is your L shell, and this is your K shell. All right, so this is N, M, L, K. All right, so the alpha we would say is the next nearest transition from, if it goes from L to K, if it goes from L to K, that would be alpha. If it goes from M to K, it would be K beta. And if it goes from N to K, it would be K gamma, which is quite rare. Now, here we can see it's the transition to the next nearest level. So it will be L alpha. From here, from N to L, it will be L beta. So alpha, the first nearest transition. All right. So these are energy sub-levels. All right. So, and if you extend this, and if you write this, it will be M alpha. All right. So the electron transition taking place from M shell to K shell, will emit your K beta type of radiation, X radiation, right? So M shell to K shell, the naming would be by the K shell which it is impinging into, which it is transitioning into, and depending upon which level, from which level it is transitioning, the alpha, beta, gamma will be named according to that. So from M to L, it will be K beta. So the answer is your K beta type of X-ray radiation. All right. So now, which of the following metals is used to filter out a beta component from copper X-ray radiation? So this is the sort of, if you write it, so this is the sort of, this is wavelength, this is by alpha mass ratio. Okay, so this is the typical graph, that is C for your nickel, for nickel. This is the absorption spectrum. So here, right around this point, there is a drop in the spectrum, right? This is where this wavelength or radiation of these wavelengths are absorbed, right? So this is the absorption spectra for nickel. So this is if the radiation spectra for, now I'm drawing the radiation spectra for copper, right? So this is the, this is copper K beta, this is copper K alpha, right? And okay, so now if this is the absorption age for copper, for nickel, so by that token, what happens is that copper K beta and K alpha, if they are emitted, they only the copper K beta will be absorbed by nickel, right? So in that case, it is used as a filter for when you are trying to emit copper alpha, copper beta radiation. If you want to filter out the copper beta radiation, so utilizing this absorption edge of nickel, where it absorbs this copper beta radiation, K beta radiation, it is used as a filter in those sort of systems. So Which of the following metals is used to filter out K beta component from copper X-ray radiation? The answer would be nickel, right? So nickel. So absorption age means when if you will impinge an electron on a certain material, which is the target material, let's say here for copper, so it will emit radiation, right? Some from the higher energy levels, alpha and beta radiations, K alpha, K beta radiations will come. But if you place a nickel filter, it will have this copper beta or K beta absorption radiation absorbed. So that is why it is used as a filter. All right. Which of the following statements is or are true about the characteristic K radiation peaks in X-ray radiation? All right. So now alpha would be, alpha 1, 2, 3. That is basically from the L level, because from just adjacent to K level is the L level. So L is also subdivided into 3 levels, right? So from L, so this is M, this is certain, okay, and this is L. So this is M, this is L, this is K, right? So this is L1, L2, L3, I might write L1, L2, L3. So adjacent from this L1, this is this, right? This is this, and this is this. This is basically would be K beta. All right. This is K alpha 3, K alpha 2, and K alpha 1, depending on which level it is coming from. All right. So all right. So now you know that H nu is equal to EV, right? So H nu is the energy, higher is the energy. Now lambda, the wavelength, is C over nu. So higher is the frequency, this is energy, this is energy, H nu is energy, this is your energy, H nu is the energy, then higher is the energy, lower will be the wavelength. All right. So the highest energy here is for K beta. So K beta, these two options remain, and the highest energy among the sublevels of L is coming from L1, which is K alpha 1. So basically K alpha 2 will have lower energy than K alpha 1 and also K beta. So the lambda for K alpha 2 will be greater. So that is why lambda of K alpha 2 greater than lambda of K alpha 1 greater than lambda of K. Alright, higher is the energy, the lower is the wavelength. K beta has among them the highest energy. So that is why the wavelength will be the smallest. And K alpha 2 and K alpha 1 among them, L alpha 1 has higher energy. So the wavelength will be smaller compared to your K alpha 2 radiation or lambda. Okay, so the correct answer would be your lambda K alpha 2 greater than lambda K alpha 1 greater than lambda K beta. Okay. So the next question is, which of the following X-ray? Let me just check. Somebody question, and please feel free to ask questions. I will repeatedly say, if you have any problem in your understanding, please interrupt and ask. Okay. So this is the following X-ray radiation is most suited to characterize iron containing materials. All right. As you know, so it depends on how high. So basically you are producing X-ray and you are trying to do a measurement on some other material. Okay. So depending on this energy, higher is the energy. Let me just write, higher is the energy, lower is the wavelength. All right. So lower is the wavelength. So what happens is that if you produce an X-ray, let's say from any target material, if you produce an X-ray, so that is this energy sublevels are being occupied, let's say. So energy sublevels are being occupied. So in this case, let me just, okay, so this energy sublevels are occupied. Okay, now you supply an X-ray impinging energy. All right, X-ray impinging, let's say from any target material. All right, it goes to a higher energy level, it gets carried out, and some, so this is absorption of energy. So some electrons will be transferred from this to this. All right, and now if it's uh, transition, depending on how from which levels it is transitioning, this is another energy level. So if it has to transition onto the another material which you are measuring onto, so it can transition from this, depending on, so it can transition from this to, all right, this. So this h nu, so this energy h nu, so this is energy h nu, this is energy h nu. So if this energy is higher than the emission energy of this transitioning from this sublevel to this sublevel, so if h nu is greater than h nu time, you'll have secondary X-ray generation. All right, okay, so it will have, you have secondary X-ray generation. This is not quite right. What you have to do is, for secondary, to stop this secondary X-ray generation, you'll have higher wavelength, right? I mean lower energy. Okay, so lower energy X-ray has to be impinged so that your X-ray generation, secondary X-ray generation is prevented, because you do not want your generation of secondary X-ray that will fiddle with your measurement, because you are trying to measure on a certain material and you don't want an extra source of X-ray. All right, so X-ray radiation is more suitable for iron containing materials. So for cobalt and chromium, their energy is lower, okay, and their lambda is higher. Consecutively, energy is lower, consecutively would mean that the lambda is higher, the wavelength is higher. So you have to use chromium and cobalt for this purposes when you are doing some measure iron containing materials. Because let me just give you some so for copper, just give you some numbers. So copper K alpha is 1.54 angstrom. Okay, lambda iron or K is 1.74 angstrom. So basically copper has higher energy than compared to iron, right? So that is why they have lower wavelength. So basically it will move to a higher energy level and there will be secondary generation of X-rays. All right, so you want to do some experiment on, let's say X-ray diffraction. So in that case you move to a higher energy level and there will be production of secondary X-ray generation, because you'll move from some lower energy level to some another lower energy level, like as I showed in this case. So there will be secondary X-ray generation. But for, let me give out this list. So for molybdenum, this wavelength of transition is 0.71 angstrom. For copper, it's 1.54 angstrom. For cobalt, it is 1.79 angstrom. For iron, it is 1.94 angstrom. Chromium is 2.2 angstrom. So in around this iron, there is cobalt and chromium, which is larger, this one slightly lower. So you cannot use this to have this of iron material. So chromium K alpha and cobalt K alpha should be useful. All right. Now the next question is, which of the following is or are true for crystal method? So for crystal method, this is very informative question. So wavelength of X-rays is fixed, all right, and the diffraction angle is variable. Wavelength of X-rays is fixed and diffraction angle is variable. All right. Which of the following methods can be used for determination of crystal structure of a single crystal? So for single crystal, you have a specifically defined crystal plane. So in Lau method, you basically change the what we call Lau method. You change the wavelength or variable wavelength method. And rotating crystal method, you do not change the wavelength, but you change the uh, you know orientation of the crystal, like you rotate the crystal, rotating crystal method. So basically single crystal uses this type of methods where you do not need to have. For powder methods, what happens is that you have different types of orientation planes. So even if you don't change the wavelength or you do not change the rotate the crystal, you'll have some kind of diffraction peaks. All right. So but for single crystal, you have well-defined crystal planes, and now you have to choose which crystal plane you are getting the signal from, and that is why you use the Lau method and the rotating crystal method. You either rotate the crystal or you change the wavelength. All right. So that would be your Lau method and the rotating crystal method. Okay. Now the short wavelength limit in angstrom for 15 kilovolt XLT voltage is, you know, you have to use this formula. H nu is equal to E B. So H is the Planck's constant, nu is the frequency of the radiation, and E is the electronic charge, and V is the voltage applied. So you apply a voltage. So let me just show you the picture already. So you apply a voltage in this, okay, and electrons are bombarded into a target material, and that does the emission process. All right. So in that case, this is the formula. So energy is equal to the potential difference or the voltage applied times the electronic charge. Okay, that will give you the equalization on different on the two sides energy dimension. Okay, so now lambda is C over mu. So basically this is CH by EV. Right? So that is 3.8 into 10 raised to 8 meter per second, 6.6 into 10 raised to minus 34 joules per second, and 1.6 into 10 raised to minus 90 coulomb times your voltage applied is 15 volt. It is 15 into 10 raised to 3 volt. Okay, that will give you the value in SI units. Like you have used all SI units, so basically your value will be obtained in SI units. Okay, the unit that it carries will be in SI units. So calculating it, what we will get is, let's see, 3.8 into 10, sorry, 3.8. You'll calculate with me also and check if I'm saying it correctly. 6.6 into exponential minus 34 divided by 1.6 into exponential minus 19 divided by 50 into exponential 3. That is your, okay, the right answer is, so 11. Okay, I made a mistake somewhere, I think. So 3.8 into exponential 8 into 6.6 into exponential 34 divided by 1.6 into exponential divided by 50 exponential 3. That's it. Okay. Mistake somewhere, I think. So lambda is needed, right? So 3.8 kilovolt, right? So yeah, now I think I got the correct answer. That is, okay, we got the answer is 0.826. So that is the correct answer. You would get Okay. 6 inch. That is correct. Yeah. Okay. So 0.826 here. So use this equation and you get this answer, right? Okay. So the Bragg's angle for 1-1 reflection for a from a FCC structured material is 24.6 degree when it is exposed to X-ray wavelength of 1.54 angstrom in a diffraction experiment. What is the lattice parameter of the material? So let's just check if there's a question. So you are getting the numericals right. Is it the case, right? Okay. So basically what you use is that, so let me just flash a picture in front of you. So this is the ellipsis, right? So this is 1 0 0, this is 1 1 0, and this is 1 1 1. So for face centered cubic structures, for 100 plane, you have in between the plane you have your one plane that is extra, that is this is a by 2. So at the a by 2 position you have the 100 plane compared to a simple cubic, all right, because there are atoms at the face centers. Also for a by 2, this is 1 squared plus 1 plus basically this is your formula, I squared by a squared plus k squared by b squared plus a squared by c squared. So for simple cubic, ABC are same. So a by dot h squared plus a squared plus l squared. So this is simple cubic, right? For face centered cubic, what you have for the 100 plane is that you have a atom plane in between. So not simply a, you have to put a by 2. So you have to put a by 2 to have this. Okay. Right. So and now for the 111 plane, you have atom planes, but you have to travel all the distances up to a on each side. So basically you have a by 1 squared plus 1 squared plus 1 squared is a by 2. In this case, this is a by 2, 2, because this case also you don't have this. So for simple cubic it was like this because there are no atom planes in between. For face centered cubic you have atom planes, right? For because they are lying on the center of the face centers. So basically you will have a by 2 root 2 not as a. Okay. So coming to the question at hand. Okay. So 2d sin theta is equal to in lambda. So can you put 1? So lambda, if you have already to minus 10 and in angstrom it is says so 1.54. So for 111 for AC structured material it is 2 into a by root 3 into sine 24.6 degree equals 1.54 into a minus 10. So basically you have to use the Bragg's law. So basically you have to use the Bragg's law. Alright, so center is n lambda. So for 2, let us just calculate 1, 5, 2, 6. So that is comes out to be 3.2 angstrom, right? So the lattice parameter is 3.2 angstrom. Is 10 raised to minus 10 meter, which is 3.2 angstrom. Okay, so the correct answer is here 3.2 angstrom. Please reach. Okay, so basically what I showed you is that like for one, it is also a by root 3 also. So you see the difference when it comes to 1 1 0 and 1 0 0. You have atom planes, you have the atom sitting at in face centers also. So basically if you do this, will not be any atoms in. So you have to have the maximum number of atoms in those planes. So basically you are considering this as the 110 plane. All right. So just because in that case it is only a by root, not a by root 2 but a by 2 root 2, because the effective distance that it has to cover to have this plane is a by 2. So a by 2 root 2 is the answer for 110, and 111 is same as the simple cubic. It's 11 a by root 3. So that is the answer. So 13, the interplanar spacing between the 110 planes of a cubic lattice with lattice parameter 3.9 strong. For cubic lattice, so basically 110 plane. So for cubic lattice, we know that it's a by root over a squared plus a squared plus a squared plus b interplanar spacing. So a is 3.9. So basically 110 plane. So 3.9 angstrom divided by 110 plane. 110 plane means 1 squared plus 1 squared plus 0 squared, that is 3.95 root 2 angstrom, which is 3.9 divided by root 2 would be 2.75 or around 76. So that would be the correct answer. This is around 2.76 angstrom. This is really simple, and I think it has a problem with this question, but what you have to see is that an X-ray beam of wavelength 1.54 angstrom is incident on a face-centered cubic crystal of lattice parameter 2.8 angstrom. What will be the closest value of Bragg's angle of second order 110 deflection? Second order, so 2d sin theta is n lambda. So 2d sin theta is n lambda. So n equals 2, right? Lambda is 1.54 angstrom, right? A is 2.8 angstrom. Now we have to find theta, right? So theta is what? Okay. So for center 110, so the d, the internal distance, as I already mentioned, is a by 2 root 2. That is already understood. If you have any problem, please interrupt me. So this is a crucial to understand. So this is 2 into a by 2 root 2 times sine of theta is equals to 2 into lambda is 1.54. So it is already given 2 into 2 divided by 2 root 2, and sine theta is equals to 2 into 1.5. So basically both on both sides this angstrom not converting into meters. So 20 angstrom, 45 angstrom, both will answer. Alright. So that is the case, but I highly doubt, because this is not fetching me the right answer. So you all can check and let me know that if you are facing any problem, because I don't think the question is. Yeah. What? Can you repeat, Simran? Hello. You are saying something. Huh. कौन सा? Oh, 12. हाँ हाँ. हम्म हम्म. हाँ 3.2 ही आंसर है. हाँ अच्छा ठीक है ठीक है. That's not a problem. But I'm saying that question number 14, because when I was working it out, right? So if you see that sine theta is coming greater than 1, okay, so that should not be the case, right? So this will cancel out. So let's see, 2 times 1.54 is times root 2 is 4.355 divided by 2.8. So it's 1.55. Sine theta is greater than 1.5. So I don't think the problem stands. Maybe I am making a mistake, but I don't find out where I'm making the mistake. So basically, we have to be check. I want to find out what's the problem, because you all can check out 2d sin theta is n lambda. So basically what they have said is that the second order 110 reflection, right? So n is 110. So if maybe uh, um, if I find out, I'll write to you people. Uh, but I don't think it's the problem stands right now correctly. So y'all can check, okay? So I'm skipping this 14 problem and moving on to your 15. Okay, so but the formula you are able to understand, right? Like the Bragg's law, and why it is d is interplanar distance is a by 2 root 2 because beyond this point, like for simple qubit, this is the 110 plane, right? But for the face centered qubit, this is absolutely not the case because you have atom planes in between. So you have to include that plane, and that's just because it is midway between the two sides. So it is a by 2 in place of a. Okay, so that is why it is a by 2. Okay, so please you can work it out. Now, pick out the correct statements. Diffraction occurs in a specific direction along which the constructive interference occurs, which is quite true because constructive interference only brings out the diffraction pattern. It's not a reflection because reflection occurs at every possible angle, but diffraction does not because 2d sin theta is equals n lambda. This will not be satisfied by every angle, right? So this is correct. X-rays can easily penetrate the metals because they have longer wavelength, which is not the case. It will have longer wavelength means shorter energy. That is the reason that it will not penetrate the metals. Okay, that is not the correct answer. C. Modern X-ray diffractometers use a scintillation of or CCD detector to record the charge coupled device. CCD means charge coupled device. So it uses charges to detect images or the intensity that is recorded. So in our lab, we work with CCD detector where where a photon is captured, right? So these CCD detectors, they capture photons or light. Basically, they are photons. They capture this photons, and if you have to image this, you can always image this, right? So you can image a sample. So CCD detector is used to record the angles and intensities of the diffracted beams. So this is correct. K beta radiation has lower energy but high intensity in comparison to K alpha, which is absolutely not correct because K alpha has lower energy. That's why it has higher wavelength, right? And K beta has greater energy. It has lower wavelength. So radiation has lower energy. This is not correct. Okay, so A and C are correct for this. So I am putting this as a disputed question. I don't know if I am able to solve it. I'll write back to you people. So we are done at this point. Okay, so question as I said, yeah, Simran, please go on. 7, right? 7, 7, 11. Okay, so see, you have to look at the transitions. Okay, so N, L, and K, these are higher levels, right? Okay, so H nu equals C EV. So basically, if you have higher energy, you have lower wavelength. Okay, so this option is correct because this L sub level, this is divided into 3 sub levels, right? L1, L2, and L3, and depending on which level it is coming from. So if it's coming from L to K, it will be K alpha. If it's coming from M to K, it's K beta. So alpha corresponds to the nearest level transition, which is nearest to K is L. So that will be K alpha transition, all right? Okay. And next nearest would be M. So that will be K beta transition. Then the nomenclature is like this. Now, if you have higher energy from L1 has this difference in energy for L1 and K will be higher compared to L2 and K, right? Hello. Yeah. I'll explain question number 14 also. Okay, so I'll get back to you. Let me just explain 7, 11, and then 14. Okay. Yeah. Can you please unmute yourself? So Question number 2. Already given the answer, sir. It's the amide group. Okay, please can you unmute yourself? Okay, let me just uh, uh okay. Okay. So yeah. So where was I? Question was right. Uh, so for this type of transition, L alpha, the energy difference between L1 and K would be greater compared to L2 and K. So wavelength for lambda K alpha 2, which is corresponds to energy difference between L2 and K, would be higher, right? The wavelength, because the energy is lower. Compared to L1, its energy is higher than L2, so its wavelength will be lesser. And among them, K beta will have the higher energy difference, highest energy difference, because it's transition from M to K. So correspondingly, its wavelength will be the lowest. Okay, so that is the reason lambda K alpha 2 greater than lambda K alpha 1 greater than lambda K beta. Okay, so is this clear, Simran? Okay, so it all depends on the energy difference. All right, so if the energy difference is higher, so it's the inverse relation for wavelength. It's the direct relation for frequency, but it's the inverse relation for wavelength, as you know. So C is nu lambda. Okay, so you asked about question 11. Okay, and also I have to explain question number 3. Okay, that's nice. So let me answer question. So we have this formula, H nu is EV. Okay, so lambda is C by nu, right? So basically what you have here is nu is EV by H. All right. So lambda will be C times H by EV. Just do this calculation and get the result. Okay. I'll not give you the answer like how am I getting it. Just do it by yourself, because this is the formula. So H nu, if H nu is the energy, this is the energy of the impinging electron, and it is triggered by voltage difference between, if you see this apparatus, if you see this schematic, if this voltage difference is triggered by this impinging of electrons, how fast they are going to be, how energy they are going to have, will be dependent on how high voltage you have applied, right? So that will define you your H nu times equals EV. Okay, that will give you your, okay. So just work it out. It's fairly simple. So now, okay, fine. Okay, fine, that's fine. So answer question number 3, the vulcanization of natural rubber, right? So basically what you have is, this is the uh, bare structure for rubber, natural rubber, right? Isoprene molecules. So this is one chain and this is another chain. So if you do a vulcanization process, what happens is that sulfur occupies these sides. They are the cross linkings between two polymer sort of chains. Okay. So basically it had this double bond. Now if sulfur is attached, it will no longer have this double bond, because sulfur has come to this place and there's an additional bond. So basically carbon will have 4 covalent bonds. So basically instead of having a type double bond, it will have another single bond with sulfur, and this carbon will be attached with a single bond. Okay, same goes with this double bond. So sulfur acts as this cross linking with the natural rubber, and this process is called vulcanization. So vulcanization with sulfur treats the natural rubber and makes it hard enough. Okay, so question 3. So Venkateshan, what I said is that question 14, it does not look correct to me, as I said. So it's not about the answer. Please try to understand that you have this Bragg's law, right? Just 2D science in lab. So what is said is that an X-ray beam of wavelength 1.54 angstrom. Okay, so 1.54 angstrom is the lambda of the impinging wavelength of the meaning X-ray. Okay, and it is said that it is a second order reflection. So it's a second order reflection, that means n is 2. Okay, and your lattice parameter given is 2.8 angstrom. So now what you have to put additionally is this interplanar distance between the lattice planes of the 110 system. Okay, and as I already said that for FCC type crystal face center tube, your interplanar distance is a by 2 root 2. Okay, so a by 2 root 2 the interplanar distance, d is a by 2 root 2. So a is 2.8 angstrom given. So just put it and try to find the answer, because I said it's a disputed question just because of the fact that sine theta here, if you calculate it, will be greater than 1, which is non-physical. Sine theta can't be greater than 1. Okay, so that's why I'm putting it as a dispute question. I don't know. I have not been able to solve it. Just please try to look into it. Okay. Yeah. Any further question from anybody? Yeah. Oh, good references, right? I have your email, right? I'll send you the okay. Do I have your email? Okay, okay. You just send it to me and I'll give you the reference, because as I've been telling, I'm sorry for that because last week has been too hectic. So I'll upload the video also, just for your sake, that you will get to know how it's solved and all that. Uh, and I'll give you the reference books. Okay. I'll definitely give you the reference books. Okay. 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 Yes. Okay. So any further question from anybody? Okay. Thank you. Thank you. Yeah, yeah. We'll conduct it in the next coming session. Okay, that will be the last concluding yeah session would be. That will be the concluding session, because this is an 8-week course. So after that you'll have your exam maybe. Okay. So shall we wrap up? Okay then. Okay, fine then. We should wrap up. Okay, okay. I got it. I got it. Okay, I'll send you. Okay. So even it's also not a problem, right? If I send you over WhatsApp or okay, okay, okay. Because e emailing is a difficult task also. You have to open your email. Okay, okay. No, no, no. It's you should also not put it right there. Huh? Yeah, yeah. Okay, 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 okay. Fine, fine. Okay, fine. Thank you.